Hello everyone, welcome to another kinetic tutoring episode. Today we're taking a look at this practice problem from a former AP test in order to hone our AP Physics C skills and abilities. So let's just get straight into it. Triangular rod shown above has length L, mass M, and a non-uniform linear mass given by the equation lambda is equal to 2m over L squared x, where x is the distance from one end of the rod. Using integral calculus, show that the rotational inertia of the rod about its left end is ml squared over 2. Alright guys, so we know that the formula for inertia is integral of x squared dm, and what we want to do is find we want to find dm in terms of dx. Since we're given a rod, we can assume that it's just simply a two-dimensional rod. So we're going to have dm over dA, which is its area, but since we're just assuming it's a two-dimensional object, we can say dm over dx, where x is its length from 0 to L. And we're also already given an equation for the density, 2m over L squared x. So from here, in order to go from dm to dx, we're going to separate the variables. So we'll get that dm is equal to 2m over L squared x dx. And now we can plug this in for dm. These are all constants, so they can be left outside the integral. 2m over L squared x cubed dx. This will give you 1/4 x cubed. We're evaluating from 0 to L, so it'll give you 1/4 L cubed. So we'll get 1/4 L cubed times 2m over L squared. This is gone. This will turn into a L squared. This m cancels with this m, and oh, hold on. Sorry, there's no m's that cancel out. I don't know what I was doing there. This 2 and this 4 factor out, and we're left with ml squared over 2 as the equation requires, or as the solution requires. So there you go. That's how you would prove this. And the next part asks us for the inertia total. So if we know the inertia of 1 is ml squared over 2, the inertia of all three of the rods is going to be this times 3. So we'll get 3 ml squared over 2. There's also a hoop, and the hoop has a rotational inertia of ml squared. So we're going to add that as well, and we'll get 5 ml squared over 2. There you have it. And now it says the hoop rod system is initially at rest and held in place, but free to rotate around its center. A constant force is exerted tangent to the hoop at a time delta t. Derive an expression for the final angular speed of the hoop rod system. Alright guys, so in order to find the omega, we're going to first start by finding the alpha. So we're given I alpha 5 ml squared over 2. This is our inertia. Alpha will be equal to force times radius, which is just L. You can see that these L's cancel out. So we'll see that our alpha is equal to 2F over 5 ml. And from here, if we know that alpha is just d omega dt, so if we integrate both sides, we'll get that 2f t 5 ml, delta t is equal to our omega. So there you go, that would be your answer. So let's move on to the next part. The hoop rod system is rolling without slipping along a level horizontal surface. The angular speed omega found in part C. At time t is equal to 0, the system begins rolling without slipping up a ramp as shown in the figure above. On the figure of the hoop rod system below, draw and label the forces. Alright, so we know that we have gravity acting on the object at its center of mass. Downwards, this is the force of gravity. There has to be a frictional force for it to roll without slipping. That's going in the opposite direction, force of friction. And then we also have our normal force going this way. And normal force is always perpendicular, so that justifies that. Force of gravity downwards, and force of friction is always parallel to the plane. And the last part is asking us to derive an expression for the change of height of the center of the hoop from the moment it reaches the bottom of the ramp until the moment it reaches its maximum height. Alright guys, so in order to do so, we're going to apply our energy, our knowledge on energy. So we know that we have some rotational kinetic energy, 1/2 this is our translational kinetic energy, 1/2 mv squared plus 1/2 I omega squared, and at the end we have mgh, where h is the height that we're looking for. So what it's telling us is that we cannot have v as a variable. It's asking us to have it in terms of omega, but we know that omega, or v, is just r omega, so we can just replace v with that in order to meet its requirements. And we know that the radius is just L, so 1/2 m r omega squared plus 1/2 I omega squared is equal to mgh. And from here we can divide by mg in order to get our h. We'll get 1/2 mr omega squared plus 1/2 I omega squared over mg is equal to the change in height. So there you have that. Let me just make sure that all the variables are correct. So the r and l are interchangeable. So when I wrote r, what I meant was l. So we can have m, we can have l, we can have omega, we can have inertia, we can have mass, and we can have the gravitational constant. So there you go. That's how you would go about solving this problem. And yeah, hopefully this was helpful. Hopefully you guys learned something. If you have any further questions, make sure to leave them down in the comments below. I will try my best to answer them. And yeah, hopefully I catch you guys later.